nothing All right. Welcome back. Um, from the break. I hope everyone had a good break. Had a although it's a relatively short spring break because of the outbreak. Um, I hope everyone stays safe and stay healthy. Um, um, I think we will get past this outbreak very soon. Right. A couple announcement is that exam 3 is approaching. It will be next Tuesday. Uh, the exam 3 will be on Lumen, completely online like exam 2. Except this time you have to upload your work on Lumen as well. All right. Basically, whatever you whatever the question you whatever your work is for the exam, you scan it and you upload it on Lumen. All right. If there is a question you had answered but without work, basically you get no credit. All right. So this Thursday would be the review session. Basically, we just do some exercises that are relevant to the exam on the class. You can ask me any questions as well. Basically, you know, it's a standard review session, right? Any questions? Yeah, I agree. If you have a drawing question, I would prefer you draw on your paper rather than draw on the Lumen. So it's okay to leave it blank in the Lumen, right? If you prefer to draw in the paper. Um, but yeah, you need to have the work. So yeah. Alright. Okay. Today we'll be doing lecture 19, which is double angle identities, half angle identities, and trigonometry equations, right? So a little bit of a review. Right? A little bit of a review is what we did last time. All right, we have sum and differences identities for sine and cosine. Basically, is for sum identities when you have the sum of the angle inside cosine, you can break it down into cosine and sine of the angles. Right? For difference as well. Right? One trick of memorizing these identities would be for cosine, when you have the sum, it becomes difference. And for sine, when you have the sum inside, it stay as the sum. Okay. However, for sine, is mixed up, right? You have sine alpha and cosine beta, and cosine alpha with sine beta. But for cosine, cosine stay with the cosine, sine stay with the sine. Okay. Sine with the cosine, sine with the sine. Same thing as the difference identities. And for tangent, basically you apply the some identities for sine and cosine and simplify, you get something like this. And for difference, it's the same idea, but the simplification might be a little bit tricky. And lastly, we have the cofunction identities. Basically, you can write the sine in terms of cosine, same thing as a cosine, write it as in terms of sine. Right. So the first thing we'll do today will be the double angle identities. Right. Basically, double angle is when you have the double of the angle inside sine, cosine, and tangent. Right. But remember, 2 theta is basically theta plus theta, right? And this is the sum identities for sine. Remember, for sine, it's mixed up, so you have sine theta times cosine theta, but the sum remains as sum. Again, another sine theta, cosine theta. Right, these two are the same thing, so basically it's 2 of sine theta cosine theta. All right. So for cosine of 2 theta, again, it's another sum identities of cosine. But for cosine identities, the cosine stay with the cosine and sine stay with the sine. Another one is when you have the sum, it becomes difference. So it's cosine square minus sine square. And then we can replace cosine square by the Pythagorean identities with 1 minus sine square. So it becomes 1 minus 2 sine square theta. Or we can replace sine square by 1 minus cosine square. And the whole thing becomes 2 cosine square minus 1. Right. It is the last two that are most useful, right? Because it has only sine or only cosine. And for tangent is the identity reads tangent theta plus tangent theta 1 minus tangent theta times tangent theta. All right. And when you simplify, it becomes 2 tangent theta over 1 minus tangent square. Okay. Any questions? So for half angle identities, basically what we will be using are the double angle identities for cosine. So let me write it down. All right. So in this case, because we're dealing with half angle, so basically what we want here is half angle, and we start from a full angle. So let's replace our 2 theta I by theta, and our theta by half theta. Okay. So if we want the half angle for sine, right, then we solve for sine of theta over 2 with the cosine. So basically you have cosine of theta equals to 1 minus 2 of sine square of theta over 2. So we move the cosine theta to the right. You have 1 minus cosine theta. And minus 2 sine square theta to the left. You have 2 of sine square theta over 2. Then divided by 2 sine. And finally, you have the square, so you have to square root sine. Right. Then we have sine of theta over 2 equals to square root of 1 minus cosine over 2. Okay. Similar idea, you can get the cosine as well. Right. So now you use the second equation. Cosine of theta equals to 2 of cosine square of theta over 2 minus 1. All right, so first we add 1 to the left, then we divide it by 2 on both sides. Right, now you have the square, so you square roots both sides. So now you have cosine of theta over 2 is equal to square root of cosine theta plus 1 divided by 2. Okay. And for tangent, remember tangent is equal to sine over cosine. So you divide these two radicals and you simplify into 1 minus cosine over 1 plus cosine. Okay. Any questions? Okay. Another way of looking at these half angle identities is the power reducing identities. All right. So if you have sine square, you can represent it with only one power of cosine. Similarly, for cosine square, you can represent it with only one power of cosine. Same thing for tangent is a fraction of only power 1 function. All right. So let's do some exercise. Okay. So for the first one, you have full power of cosine and full power of sine. So the first thing is to treat like this. Let's do only the left hand side first. Okay, and this is a square minus b square. So basically is equal to a minus b times a plus b. Then for this part, cosine square plus sine square, that's Pythagorean's identity, which is equal to 1. And for this part, right, that is the formula for double angle on cosine. So this is cosine of double angle 2 theta. So 1 times cosine 2 theta is cosine of 2 theta. And the right hand side is also cosine of 2 theta. Therefore, left hand side is equal to the right hand side. Okay. Any questions? Okay. So the next question is we have a cosine theta to the fourth power. Okay. And we want to have sine and cosine that has the power at most 1. Right? So we want to reduce the power. So the first thing is to recognize the fourth power by the square of a square. Right? And we have the power reducing formula for the cosine. This is basically cosine of 2 theta plus 1 divided by 2, and then square. All right. The next thing is to expand the square. You have over 4. The top is cosine square of 2 theta plus 2 times cosine of 2 theta plus 1. Okay. And the cosine square 2 theta has power 2, and we don't want that. So we reduce the power again. That is cosine of 4 theta plus 1 divided by 2. That is the cosine square of 2 theta. And since everything else has power 1, we can keep it like this. Okay. All right. Of course, you can do another simplification of bringing the 2 to the fraction 2, get rid of the fraction 2 here by multiplying 2 on both sides of the fraction. Cosine of 4 theta plus 1 plus 2, you have plus 3 plus 4 cosine of 2 theta. Now everything has power at most 1. 1 power, 1 power. Instead of the 4 power right here. Okay? Does that make sense, everyone? So basically here you use the power reducing identities right here and right here. Use it twice. Next one, you have a sine of 4x. And sine of 4x is just double of 2x. So you apply the double angle identities first. So that is 2 times sine of 2x times cosine of 2x. So that is a double angle formula for sine. That is the first step. The next step is you do the double angle identities for sine here and the cosine here. Right. After you do the sine of 2x becomes another 2 times sine x cosine x. And cosine of 2x, you can use either 3 of them. Right. In this case, I would use the cosine square minus sine square. All right. And you can simplify this, put these 2 together. So this is 4 sine x cosine x times this is sine x cosine third power minus 4 times sine x cosine x times sine square. So you have right, third cubic power of sine times cosine. Right. Any questions? Right. That is the identities the double and half angle identities for the trig functions. Okay, and next we will be dealing with the trigonometric equations, right? That is the equation with sine and cosine and tangent, trigonometric functions like this, right? So one of the example would be right. So so now, for example, you have the equation sine x equals to 1/2, right? So first we look at the graph for sine x. So remember the graph for sine x, it looks something like this, right? has the maximum in 1, minimum in -1, 0 at 0, pi, and 2 pi. Right. So when sine x equal to 1/2, you just look at the intersection with y equals to 1/2, right? So you immediately you see there are two intersections. One of them here would be the one before the pi over 2. So that is when sine x is equal to 1/2, x equals to pi over 6. Right? And the other one, when you look at the unit circle, that is 5 pi over 6. All right. So now this and this would be the solutions of the equation sine x equals to 1/2. Just simply by looking at the graph. Right? Okay. The next one is that sine x is equal to minus square root over 2. Again, we are interested in the region between 0 and 2 pi. Right? Because everything is periodical, you can just add 2 pi's and minus 2 pi, and we get all the solutions. Right? So we're only interested in the region between 0 and 2 pi. Right? So this is the graph of sine x, and we look at the intersection with minus square root of 2 over 2. Right? Immediately you look at an intersection here and intersection here. Right? By looking at the unit circle, this is five pi over 4, and this is 7 pi over 4. Right? So now you have two solutions for the equation here as well. Okay. Next one, how about cosine x equals to 0. So now the graph of cosine x is slightly different than the sine of x, right? From 0 to 2 pi, of course. Right? It starts from 0, 1, and it reaches 0 at pi over 2. The minimum at -1 at pi, back to 0 at 3 pi over 2, and go back to 1 at 2 pi. So that is the graph for cosine x. Right? And the intersection of y equal to 0, which is the x-axis, is precisely these 2 points, pi over 2 and 3 pi over 2. Right? So that becomes the solutions for the equation cosine x equal to 0. Right? Okay. Finally, we deal with tangent x. Right. Suppose you have the equation tangent x equal to -1. Right. For tangent, we are interested in the region between minus pi and pi. Actually, pi over 2 and pi over 2. Right. Because the graph looks like this. Okay. And because this is periodical, and you just repeat yeah. You just repeat this pattern over and over again, right? Because it's periodical. So we are only interested in the region between minus pi over 2 and pi over 2. Okay. When tangent x equal to -1, so basically we want the intersection with y equals to -1. And you can see that you have 1 right here. Right? And then using the calculator or whatever, or in the circle, you can find out that this is minus pi over 4. Okay. All right. So this is rather simple trigonometry equation, right? It has only one kind of trig functions, right? Either sine or cosine or tangent, and it has at most power 1. So this is relatively simple because we can just graph them. However, if we have rather complicated functions, right? In this case, if we have sine of 2x equal to 1/2, right? Then you have to graph sine of 2x instead of sine of x. Right? Remember, sine of 2x is basically having a horizontal shrinking on sine x. The graph still looks like this, except the period is shrinked to pi, and reach the maximum and pi over 4. So when you have the intersection with 1/2, right, So now instead of pi over 6, it becomes pi over 12 here. And instead of 5 pi over 6, you have 5 pi over 12. Right? Everything is shrinked by 1/2. All right. So the solutions would be pi over 12 and 5 pi over 12. All right. Any questions? All right. So when you have some complicated trig functions, always to reduce is to the form that we just did before, right? To the simple form. So for example, for the first one, if you have 2 of cosine theta plus 1 equal to 0, you want to have cosine theta on one side of the equation. So to simplify this, you minus 1 on both sides of the equation, followed by divided by 2. So now you have the equation cosine theta is equal to minus 1/2, right? Now, by the graph of cosine theta, and then you find the intersection with minus 1/2, then you can find out that there are 2 solutions here. One of them, can't do it on top of my head. So it's either 2 pi over 3 or 4 pi over 3. So these are the solutions for the equation 2 cosine theta plus 1 equal to 0. All right. Next one, you have four times sine square of theta minus 2 equal to 0. So in this case, you have the square of the sine, which is hard to do with. We don't know the graph of it, so we want to reduce the power of sine, right? By the reducing power identity, sine square theta is equal to 1 minus cosine of 2 theta over 2, right? Minus 2 equal to 0. Simplify this, you can have 1 minus cosine 2 theta minus 1 equal to 0. All right. And 1 minus 1 is 0, so you have
basically cosine of 2 theta equal to 0. Right? Now let's graph the function cosine 2 theta. So cosine of 2 theta has same graph as cosine, except everything is shrinks by 1/2 horizontally. Right? Instead of having the period 2 pi, it shrinks to pi, and the intersection instead of pi over 2 becomes pi over 3. Instead of 3 pi over 2, it becomes 3 pi over 4. Right? So cosine of 2 theta is equal to 0 is basically the intersection with the x-axis, which is this 2 points respectively. So now you have the solutions for cosine of 2 theta equal to 0, which basically is the solutions for our original equations, 4 times sine square minus 2. Right? Next one. Let's see. Have 2 times tangent theta plus 3 is equal to 5 plus tangent theta. Okay. So basically you have you want to isolate the tangent theta in one side of the equation, right? So let's simplify this. Right? Distribute the 2 into the parentheses. You have 2 times tangent theta plus 6 equals to 5 plus tangent theta. Right? Then you minus tangent theta on both sides of the equation, followed by minus 6 on both sides of the equation. Plus 6 minus 6 is gone. Plus tangent minus tangent, this is also gone. So the right-hand side becomes 5 minus 6, which is minus 1. The left-hand side becomes 2 tangent theta minus tangent theta, which is tangent theta. Right, this becomes, like before, tangent theta is equal to minus 1. So in order to solve this, we graph the tangent theta from minus pi over 2 to pi over 2, right? The graph looks like this, and the intersection with minus 1 is right here, which is minus pi over 4. So this is the solutions for this equation, which is the solution for the original equation here. So the solution here is theta equals to minus pi over 4. Okay. All right. Number 4, you have a rather complicated equation. 2 times sine square minus 5 sines theta plus 3 equal to 0. All right. So first you can factor it, or basically use the quadratic formula, right? So in this case, we use another variable to represent sine theta, right? So sine square becomes u square, minus 5 sine becomes minus 5u, plus 3 equal to 0, right? So this is a quadratic equation, right? In this case, the variable is u, right? So we want to solve for u. Using the quadratic formula, so this is 2a, which is 4, a is 2, b is minus 5, and c is 3. Right, 2a minus b on top of 5 plus or minus square root of b squared minus 4ac. Right, simplify this, you have 5 plus or minus 1. So you have one of the u is 6 over 4, which is 3 over 2. And the other one is 4 over 4, which is 1. Right? After solving the u, then because u is just sine, right? So you have sine theta is equal to 3 over 2, or sine theta is equal to 1. So you have two trigonometry functions to solve with. Okay. So let's delete some whiteboards. Anyway, so let's solve the first one. Sine theta is equal to 3 over 2. The other one is sine theta is equal to 1. So first, you draw the graph of sine. Okay. Then, if sine theta is equal to 3 over 2, that is right here, because the maximum of sine is 1. So this never has any intersection. So this is no solution. And sine theta is equal to 1 is when theta is equal to pi over 2. So this is the solution for pi sine theta is equal to 1. So the solution becomes theta is equal to pi over 2. Okay. Any questions? All right. So the last one is cosine of 2 theta is equal to cosine theta. All right, so in this case, you basically want to have cosine theta rather than cosine of 2 theta, right? Because cosine of 2 theta, these two are two different graphs, and then we can't, make it as a simple function. So we want to have everything in terms of cosine of theta. Right? So cosine of 2 theta, use the double angle formula, is 2 of cosine square of theta minus 1. Right? And then move everything to the left, you have 2 of cosine square minus cosine theta minus 1 equal to 0. Again, this is a trig function with high powers. You use another variable to represent the trig function and becomes a quadratic equation. Right? And to solve the quadratic equation here, you use the quadratic formula. In this case, a is 1, a is 2, b is minus 1, c is minus 1. So u is equal to 2a minus b plus or minus b squared minus 4ac. Okay, then this can be simplified as 4, 1 plus or minus 1 plus 8, which is 9. So it's 1 plus or minus 3 over 4. So u1 is 1 plus 3 over 4, which is 1. And u2 would be 1 minus 3, which is minus 2 over 4, which is minus 1 over half. Minus 1 half. Right. Because u is our variable to represent cosine, so now it becomes cosine theta is equal to 1, or cosine theta is equal to minus 1 half. Again, to solve trig equations like this, we basically draw the graph of the trig function. This is the graph of cosine theta. So we want to look at the intersection with y equals to 1 and the intersection with minus 1 half, right? For the intersection with y equals to 1, it basically is the starting point 0, 1. Oops. Theta equal to 0. And for minus 1/2, again, use the unit circle. This is 3 pi over 4. Oh, sorry, 3 pi over 2. Wait, 5 pi over 4, sorry. And 7 pi over 4. Wait. Oh, no. 3 pi over 4 and 5 pi over 4. Sorry. Wait. Oh, sorry. Make a mistake. This is. I'll get a different one. This is 2 pi over 3 and 4 pi over 3. Yeah, thank you, Connor. Let me see. All right. So all of the equations are all of the solutions will be the solution for the original equation. Cosine of 2 theta equal to cosine of theta. So you have theta equal to 0, theta equal to 2 pi over 3, and theta equals to 4 pi. All right. Any questions? All right, so that's it for the class. If you want, I can pull out a Lumen exercise as an in-class exercise. Okay. So you have a class exercise. Solve 8 times sine of 2 theta minus 7 cosine theta equal to 0. Right. So the hints here would be using the double angle identities on sine, and then you will have a common factor. We'll go over it in 10 to 15 minutes. All right, let's do this. So again, we use the double angle formula for sine of 2 theta, which is 2 of sine theta cosine theta something like this. And you notice that you have a cosine theta as a common factor. So we pull this out. Then this becomes 8 times 2 times sine theta, which is 16 sine theta minus, when you pull out the cosine, it left with 7 equal to 0. Right? So when the product is equal to 0, it means either one of the factor has to be 0. So you have either cosine theta is equal to 0 or 16 sine theta minus 7 is equal to 0. So you have two simple trig function to solve. To solve the first one, you graph the cosine graph, and you notice there are two intersections with the y equal to 0, which is the x-axis, pi over 2 and 3 pi over 2. So this are one set of the solutions for the equation, and the other one is sine theta is equal to 7 over 16, right? So in this case, when you graph sine theta, the graph of sine theta, there are two intersections. Oops. Here and here. When you have 7 over 16, right? So in order to do that, right, in order to find the exact value of the theta, you have to use the inverse trig. However, the inverse trig only works with the angle between minus pi over 2 and pi over 2. So that means you can only find the value for the first angle. The inverse sine of 7 over 16, which is roughly which is roughly 0.4528, right? Okay. And for the next one here is basically has a symmetry on pi over 2. Use a different color. Right. So the other theta would be pi minus the first theta. which is (2.6888). Right. I think in this case the tricky one would be finding the second angle, right? After finding the first angle you can use the arcsine. The second angle is it has a symmetry over pi over 2. So that means when they add up, it must be pi. So the other angle would be pi minus theta 1. Right? Okay. Any questions? We'll do one more and then we call it a day. All right, let's go over this. So in this case, you have cosine and sine, all right? There are two different functions. You don't want that. So basically, you have to convert one into the other one. So the easier way is to convert cosine square into sine function, right? By using the Pythagorean's identity, sine square plus cosine square is equal to 1. Right? So it becomes 1 minus sine square theta is equal to minus 4 sine theta. Move everything to one side of the equation, it will becomes 0 equals to sine square theta minus 4 sine theta minus 1. Okay, so this is similar to what we did before. All right, you just replace the sine theta with a variable, let's say u, and then let's see. Right, so when you simplify this, when you simplify this equation, what we are doing here is we minus 1 on both sides of the equation to get rid of the plus 1 here, and plus sine square theta to get rid of the minus sine square. Right, so that's why you have plus sine square theta and the minus 1 on the other side of the equation. Right, so this is negative 1. Okay. So now you have u equals to sine theta. You replace everything by u. So we have 0 equals to u squared minus 4u minus 1. Okay. Then you solve by using the quadratic equation, I mean the quadratic formula. Right? Which is right. I skipped the algebra of the you know, A is this case 1, B is minus 4, and C is minus 1. Okay. All right. So therefore, you have one of the u value be 2 plus radical 5, and the other one is 2 minus radical 5. Right? So that means sine theta would be 2 plus radical 5, or sine theta is 2 minus radical 5. So let's draw the graph of sine. That's maximum 1 and minimum minus 1. Where is 2 plus radical 5? 2 plus radical 5 is somewhere here. It's 4 point something, right? It's definitely greater than 1. So as you can see, it has no intersection with the sine theta. So this has no solution. Right, how about the other one? The 2 minus radical 5. 2 minus radical 5 would be negative something here. Right? And as you can see, there are two intersections. Okay, so how do we find this intersection, right? First, we use the arcsine of 2 minus radical 5, and then we can find an angle. Use your calculator. But when you use the arcsine, right, this will return an angle between minus pi over 2 minus pi over 2 to pi over 2. So this actually would be a negative angle like this, right? This is not what we want, right? The angle is somewhere here, right? However, because the sine is periodical, when you add 2 pi, this moves to, let's use different color here, right? So when you add 2 pi, it's actually here. It will move to this one. So suppose this is the theta 1 and theta 2, and then we can get theta 2 by adding 2 pi here. So 2 pi minus, which is 6.0449. Okay. And after we get the theta 2, we can get the theta 1 because these two angles are symmetry along, this is 3 pi over 2. That means theta 1 plus theta 2 has to equal to 3 pi. So you subtract 3 pi from the theta 2 that we just get, the 6.0449. Then you get 3.3799. Okay. So in general, the solution for the original equation would be or right. So you have two angles for this solution, right? That makes sense? Right. We'll be having the review on Thursday and then the exam on next Tuesday. All right. See you guys.